Hey, and welcome to the session, everyone. My name is Vicky, and I'm here today with my colleague Suchakra to present a tool called Yearn, which is an interactive shell for code analysis. So let's get started. First of all, if you want to follow along with the demos that we're going to be showing in this presentation, you'd want to download and extract the vulnerable code repository that we're going to be analyzing first. We're going to be using this version of the VLC, and you can download it by going to get.videolan.org. And if you want to follow along with some of the demos that we're going to be showing you, you probably also want to download and install the tool Yearn, which you can do by visiting github.com/yearnio/yearn. And in terms of machine requirements, we recommend that you have at least 5 to 7 gigs of free RAM, as well as 4 CPUs on your system. This is because we're going to be working with graph traversals and graph generation, which can get quite resource intensive if we're working with larger code bases. But this is not necessary. If you don't have these available, the analysis will just take a little bit longer to run. And you'd also want to have OpenJDK 1.8 or above installed. And on this slide, you can also find a few links that you probably find helpful if you want to use Yearn. The first link is the link to the Yearn documentation located at docs.yearn.io. And the second link, queries.yearn.io, links to Yearn's query database, where users of Yearn share useful queries that can be used to scan for specific issues in code as well as vulnerabilities. And the last link right here is the link to our Discord community. A lot of us hang out there, and if you have any questions or any queries that you need troubleshooting, you can just head on over there, and I'm sure there will be a lot of people who are willing to help. So again, my name is Vicky, and I am the developer evangelist at ShiftLeft. And I'm here with my colleague Suchakra.
Hey everyone, I'm Suchakra. I'm a staff scientist at ShiftLeft. You can find me at Texology on Twitter, and I work with the folks who have developed Yearn, and I help them do that. Thanks.
So let's first talk about what you'll be learning today. What you'll learn by the end of today is that first, you'll gain the ability to find vulnerabilities in large code bases such as the VLC. And how we're going to be doing that is that we're going to be using interactive code analysis and code exploration techniques to find really precise issues such as bad programming practices and specific signatures of vulnerabilities in your code base. And then we're also going to show you how you can convert these manual code auditing steps into a script that can be run automatically in all of your programs or your applications. You'll also learn how to, you also gain insight of how external libraries are being used by your own code. And the result of all of this is that you'll be able to stop your reliance on, vendor provided or commercial SaaS tools that don't always do what you want them to do. And instead you can use your knowledge and to formulate really precise queries to scan for exactly what you're looking for. And with that, you can find very precise issues in source code, as well as novel classes of vulnerabilities. And finally, you'll also gain some proficiency in Scala because that is the language that we'll be using to write queries in Yearn. So let's first talk about the idea of interactive code analysis. So when you look at a lot of the SaaS tools, either commercial or open source that are available on the market right now, a lot of them work in the way that you click a button and then you see what comes back from the SaaS scan tools. But what Yearn does is that Yearn flips this approach and instead allows you to specify exactly what you're scanning for. It allows you to ask questions, ask precise questions about the behavior and the properties of the code so that you can scan for very specific issues that traditional SaaS tools don't really scan for. So this is a quote from my colleague Fabian, who is also the inventor of Yearn. He says that each program is its own universe, And hacking is about exploring, documenting, and exploiting its rules. So hacking and looking for vulnerabilities isn't just about clicking a button on a SAST tool and see what the SAST tool throw back at you. It's very much about understanding the program itself and understanding what the different elements of an application are and how they interact with each other. And that's what Yearns allow you to do. Yearn allows you to um, sort of explore the code base from a security perspective. So this is very much like the interactive debugging tools that you often use, like the GDB. So we like to say that Yearn is like play pause debugging, but just for static analysis. So let's now talk about the fundamentals of programming languages. And what is even code? When you write a statement like this, int y equals x plus 50, what actually happens under the hood? So what the computer actually needs to do when you program a statement like this is that the machine needs to understand the statement. And the first stage of the machine understanding your code is called lexical analysis. And in this stage of the compiler will actually break down your tokens into break down your statement into individual elements called tokens for further processing. And then what the compiler will do next is to start understanding the syntax of the program by building these tokens into an abstract syntax tree or an AST. This process is called semantic analysis. And the purpose of semantic analysis is that it generates a data structure that can represent a structure of program code. You can see that the equal token on the left here gets translated into a node in the tree that connects y and the statement on the right here. And the add token on the left gets translated into a node that connects x and 50. So you can see that now the tokens actually have some meaning attached to it, and the relationships of between the different elements actually become more clear. And now what the machine can actually do is that it can traverse the graph to understand the relationship between the different tokens. So now what if this statement is located inside a function? How would you then represent the code in a graphical way? So you can actually represent this in the tree format as well. What you can do is that you can build something like the enhanced AST, the enhanced abstract syntax tree. And what you can do is that you can mark the tree with additional properties so that the relationship between this statement and the overall code base becomes even more clear. So you can see here that this entire statement is wrapped in a declaration, which is wrapped inside a function. And so now, what if the function becomes more complicated? Let's say that instead of a simple variable declaration, it also contains something like a conditional statement, a loop, and so on. How do you actually represent the structure of the code when this is happening? So in this case, another kind of graph representation would probably be more suitable to represent the code. So you can see here that we can represent the function with an if-else statement with a control flow graph or a CFG. This kind of graph is designed specifically to represent the control flow structure of a piece of program. So here you can see that there's a function with which defines y, and if a condition happens, then the function returns. And if another condition happens, something is called, and then z is declared, and then the function will return. And so another thing that you can use is the program dependence graph or the PDG. And this kind of graph is designed instead to show the data and functional dependencies that exist within the program. You can see here that z is dependent on y, which is then in turn dependent on x. And so what the compiler can eventually do is that the compiler will use all three of these or even more intermediary representations of code and translate the code into something else that it can understand, and then optimize the code and eventually translate the code into machine language, which will then be executed directly by the machine. But we're not going to worry about these later stages of compilation yet. For our purposes, we're actually only going to be worried about these intermediary representations of code. What you can do here is that you realize that these intermediary representations of code, like the ST, the control flow graph, and the program dependency graph, with all these representations, we actually have something that can map out different aspects and different properties of the program really well. And what we can do here is that we can combine these three types of graphs into a master graph that we call the CPG, or the code property graph, that represents different aspects and relationships of the program more comprehensively. And so until now, with a CPG, we have a very low level representation of the code. But in reality, you'll also have to incorporate higher level concepts that still impact program behavior, things like classes, methods, as well as method returns, and so on. So we also need to annotate the graph and enhance the graph with these high level information that can help make our analysis more accurate. So for instance, we can say things like there is a pie class that inherits from the recipe class that defines a foo method that calls m.bar, which is defined in another class, and so on. And this will also allow us to have a deeper understanding of the relationship between the higher level concepts of the program, as well as the relationship between the different data that's used in the program. For instance, it's only with these high level representations that we can see that when m.bar is called, data actually gets passed into baz, which is defined in the logger class. So in the end of all of this, we can realize that we can represent your program or your application in a graphical format. And by doing so, we actually gain a really powerful tool that we can use to understand the interrelationships and the properties of the program that we can then use for debugging purposes or for vulnerability hunting purposes. So the tool we're presenting today is called Yearn. And what Yearn is basically a framework for understanding code to gain insight about your code and to build tools for debugging and for security purposes. So when you feed a program or an application to Yearn, either as source code or as a binary, what Yearn does is that it actually generates this code property graph that we talked about for you. And then it provides you with a shell that allows you to query the graph for information and perform graph traversals on the graph to gain insights about the code, to find bugs for security purposes, and even find a few 0 days that are nuanced bugs that are hard to detect otherwise. So what you can do with Yearn is that you can ask questions about your code base with the shell, and then you can formulate queries that look for specific behavior in your code, like insecure coding practices or outright vulnerabilities that the attackers can exploit. And then you can convert these queries into a script that allows you to run them repeatedly and automatically across a wide variety of applications. And then finally, you can take those recipes to run again and again in your security pipeline or tools. So it's kind of like writing shell script to automate tasks. Yearn actually allows you to write queries that detect specific behaviors in code and then convert that into a script to scan across all of your code bases. So for the next part of this talk, Suchakra is going to show you some demos as well as what Yearn actually looks like in practice.
Hey, thanks, Vicky. So what we'll do right now is we'll have a short demo where we use a sample piece of code, which is VLC, and we'll navigate through the code and we'll perform some analysis over it as if a security analyst is sitting down and looking at it through Yearn. And as you can see, I've already started Yearn. Once it starts, it gives you this nice interactive shell. And what we'll do now is import the VLC code and start running. So the way to import is you would do something like import code. Now I have already imported VLC with me, so I can just do open and the graph is now being loaded from the disk, and it will soon be in memory where I can query the graph and ask questions to the graph. What we will do is we'll ask some very basic questions now. So for example, we can look at the graph. It's always invoked by using CPG. And then we can get the methods from the whole graph. So all the methods inside the graph, and then filter them by the name which has parse in it. And once we get this, we will list the names of all those methods and convert it into a list and list it. So when you do this, the query is running over the graph, all the methods are being browsed through the graph, and through each of those methods, we are now finding the names of them and listing them out. So all the queries here go from left to right. And as you can see, this is very much as a functional kind of language. And indeed it is actually completely 100% Scala. So you could find a specific method and then you could dump that method, which means like just list all of the methods which have parse sig in their name. You could also now use Scala techniques where you would basically try to map. So each of the method node here, which has parsec in their name, we can create a map of this, and we can map them by their file name and the content of that, so of that method. So basically a file name and a list which contains basically the content of that method. So this is one way in which you could start browsing methods. You can now do something more deeper, because the graph is not just browsing the methods. You could do it by any ID. So what we are doing right now is going through a method which is named as parse public key packet, and look at all the local variables inside that name, inside that method, and then name of those local variables and create a list of them. So we can see iRead is basically one of those methods. Incidentally, I also have that method open here. So you can see iRead is the only local variable that has been defined here, and we are getting this here. So we can now again use that map technique that we discussed previously and create a map of the locations where you get the line number and the file name for all those methods. So we can say it's line 108 and in update crypto.c. So this is interesting, and where this method is defined, and you can, as you can see, this is defined in line 108. You can try out all these other type of methods also. You could find the types of those local variables that you have just found, and then try to find the type. So size t, and as you can see, we have information about the method, the local variables inside it, the type of those local variables inside it. We have information about the returns inside the method, or any other variable which is either the parameter of the method, etc., etc. You can try all of these things out. We can also find who called this method by doing caller, for example. You can also find what this method is calling by doing a call.name.l. So all the calls which are inside the method, they will be listed. Here we can see who is calling this method. So if there are multiple methods who are calling each of them, we can actually find them out. And actually, let's try this out. So we will take this method, and what we would do is repeat caller, and every time you repeat the caller, you emit its name. So that's basically what this query is doing. So it will go to the parse public key method, do this thing that we did before, basically caller, and then dot caller dot caller dot caller till you reach the end, which means like at the top of the funnel. So once you run this, you can actually see we go all the way down and all the way to the main. So the main call update check real, and then they called it all the way down, and you reach this method. So this is one way to understand call chains by programmatically by using this technique. You can also go the other way around, where we try to find the callees. And as you can say, this will be very expensive, because there will be multiple callees and you're branching out deep inside. So we'll skip this one, but we can understand like how you can have these graph traversals over the graph and then start repeating them. This brings us to other interesting things, understanding about types, variables, and filtering of that. So let's look at a type called as VLC underscore. So we have some information about a type called as VLC, but we do not know that completely. And what our goal is to find all the local variables of that type and create a list of them throughout the whole code base. So, obviously it's going to be expensive. You run through the whole code base, and then you can find out all the local variables that have ever been defined in the code base, and which have VLC underscore something as the type. You can find member variables of a given struct or something like that. So if you know that there's a struct VLC log t, you can find out all the member variables which are inside that. Um, you can find the local variables and start filtering them by their type. So all the local variables where the type is VLC log t, and then list them. It's basically the same thing that we did here, but now we are doing reverse. We are going by the local variables and then finding out the ones which have the type VLC log t. Here we were doing the reverse. We were first finding the type which has VLC in its name, and then finding the local variables which are there. So as you can see, the graph is there, it's interconnected, all the variables, all the methods, all the caller callees, they're all connected. You can navigate through them in multiple ways. So for example, find local variables and filter them by their types, and then find which methods they are used in. So the methods now are connected to the local variables which are of a given type. And then also you can go all the way and try to find the file names where those methods are used. So this now looks like a very comprehensive query that you would start using when you're doing some security analysis. So you would try to find local variables where the type is VLC log t, find out which methods these local variables are in, and then find out which files these methods are in, then start listing these out through the system. And as you can see, there's this one file which is there, which has this local variable. So now we are approaching the zone where we are asking intelligent questions to the code. You can use this for understanding code complexity. So for example, identify the functions which have more than 4 parameters. So there will be a lot of functions, obviously, which have more than 4 parameters. Identify functions which have more than 500 lines and list all of their names. Functions which have multiple return statements, that's interesting. So you can find out that if there are functions which have multiple return statements, they could be of interest to you, and you can understand why we have functions which have, for example, like 200 return statements. So the function may be too big and there is too much complexity in it. You can find functions which have more than 4 for, do, or while loops. Or functions which have nesting depth larger than 3. So basically, you have a control structure inside the function, and there are more than 3 nesting depth. So you have if, else, if, else, if, else. So as you can see, in such cases, there are more chances of a developer making an error. So you can use these to identify complex pieces of code. Now, something interesting is that we can use this not just to understand what's happening in your code, but any other external library that you have, any other methods from an external library that you are trying to call. So we'll do it with VLC, and we'll see that, okay, there are all these methods, XML parser dot something, these are all coming from external libraries which have been defined somewhere there. These are not completely VLC's own defined methods which are there. And this is interesting because all the interesting part would happen somewhere here. So for example, all the calls to string copy, which are happening in your code base, you can search through this. So it will search through all the code base and it will see where all the string copies are. Obviously, there may be a lot of them. So it's basically going through the whole graph, identifying where all string copies are. You could also make it a little bit more interesting by having now more intelligent questions to it. So this is something which is very security specific. So find all the calls, so all the call sites which have sprintf in them. where the second argument is not a literal. So where the second argument is not a literal, and you try to find them out. So this is interesting because these are all and you list the code at them. So which means the line of code which is there at that time. And this is interesting because it tells you, where the second argument is not a literal, and it's a clear-cut indication that something is influencing that second argument, it's listing that the format is basically the second argument there. And you can, at that time, if you have identified something, you could just quickly dump that method directly itself, and it will tell you, okay, yeah, here is s and printf you are using, or here is s printf, where the second argument is format, and format is basically coming from somewhere else, and we can see that format is actually fine. It's a literal here. So now we can have a sigh of relief that, yeah, this is not some attacker controls thing. It has been defined inside the method itself, and it's actually a literal. So it's interesting, these nice gotchas that you can see. We'll now try to do something interesting and find some short vulnerabilities in VLC. So we have already loaded VLC. What we'll try to do is try to find all the places where malloc call is being used. So malloc is being called where the first argument has an addition operator. So what I'm doing right now here is I'll just quickly run this very specific query where we try to list all the malloc calls where the first argument is a call to an addition operator. So as you can see, this is comprehensive. We moved all the way from the graph, trying to find all the call sites, trying to find their arguments and filtering them out based on an operation that is happening. And this is interesting. So if I try to list all of them, we can see that there are many, many mallocs which are there inside the code where arithmetic operations are happening. And we are interested in an addition operation. So why are these important? So assume that like in any location, like we can take this, for example. So if you have id +1 and id is, the max integer value, which can be here. And malloc tries to now allocate max in +1 and it overflows. So the memory return here would be actually an overflow. So it would be less memory than you actually wanted it. And now just assume that you're using that memory in something, like you're trying to copy something using memcopy, or you're trying to use that memory and read data into it or read data from it. So if something like that is happening, you are going to have a buffer overflow, and you have that overflow, and there's a weakness in your code. There's a point which can be now compromised. And this is interesting. So with just single query that we gave, we were at least able to shortlist all these pieces in your code where malloc is using an arithmetic operation. So the first step is already done. What we'll do now is we'll define this query as a source, and we'll keep it with us. So this function source has been defined. You can always do source.code.l, and then suddenly you will see the same list. We also have now multiple mem copies, and we define these mem copies as sinks. And it's not just those mem copy calls, the arguments which are going inside those mem copy calls, we will define them as sink. And then we can do sync reachable by source dot sync reachable by flows source.p. So what this does is it tries to find all the sinks, which are arguments of the mem copy, which are reachable by the mallocs having arithmetic operation. So this is itself, like a clear sight that something bad is happening. And you will shortlist all the big mallocs that you have seen by only the ones which reach memcopy. So this is the way an investigator would basically operate. And obviously this is expensive because you are first going through all the mallocs which we had just seen before, and then all the mem copies, and then trying to link where the data is flowing. So this is real data flow analysis that is running, and obviously it's going to take some time. So now, as you can see that this returned a lot of these flows, with you, and we'll look at one of them, and then we'll see how you can read these flows. So these flows are very interesting. So they start from a source and they end at a sink. This is exactly what we had defined. The source here was the malloc, where the first argument contains an addition operator. And the sink was a memcopies argument, any memcopies argument. And this is exactly what we have here. So we start tracking a malloc, which has an arithmetic operation in it. And then we start tracking the data flowing from this malloc all the way down to a memcopy. And we can see that it's actually traversing three methods. It started from an open method, went to a malloc method, and then went to parse signature v4 packet. And we can then start triaging, like what happened to this exact malloc, like where is mlen coming from. We can look inside the piece of code. We can try to find that out and see if this usage of the data coming from this malloc has been sanitized in between, has been checked in between or not. And if it has not been checked, if its size has not been checked, then we can clearly see that something bad can happen here. And it gives you all these different data flows for different methods and different libraries and different files for you to start triaging with line number and like which file it is in, so that you can begin this triaging. And this actually is not something which is only hypothetical. We actually found a bug, and that's basically what we're going to discuss next. So we recently, I think last month, we found a bug in VLC, and it was acknowledged by them and published in the VLC Security Bulletin version 3.0.13. And the bug was actually derived from the same idea that we have, like try to find all the mallocs with arithmetic operations or reaching a mem copy. It's a little bit more generalized version of this, where we try to be more specific in a given context. So we not just find out reaching mem copy, but we try to filter it out, where you have an assignment and the exact code is not a mem copy, is actually a mem copy's first argument, and it is not and the first argument of that exact mem copy is not an argument, is not the third argument of the same mem copy. So this basically makes it more specific, and the flood of these data flows that you were seeing, it gets reduced and you get a very targeted result. And basically that targeted result was actually this parse public key packet. And if you go down in this parse public key packet, and if I recall correctly, it was this I packet len. Just give me a second. It was, I think, 694 somewhere. We have this malloc here where the I packet len value, which is coming here, there's an arithmetic operation happening. So the malloc is going to return some value, and it goes inside this pointer. And this basically is being used by memcopy. So data is being written inside this. And what happens is, as we began this triaging of understanding where I packet len is coming from, we discovered that this I packet len is incidentally controlled by the value pos, which is coming from an attacker. So an attacker can, so this file specifically is the file responsible for auto updates in VLC, and the value pos can be controlled by the attacker, and they can change the value in a manner that eventually the I packet len value is max size. And if you add it to the max size, you have an overflow, and then you suddenly have a mem copy, and we had crash here. And so this was interesting, because by just automating the process of understanding mallocs having arithmetic operations reaching to operations like memcopy, we were able to actually find direct bugs. And we ran it through the system, and there were multiple such instances, which could then be later on triaged and actual bugs be found. So that brings us to the end of Yearn's demo. If you have any questions, you can go ahead and please use a Discord, and we would be able to help you there.